Hello class, this is going to be our flipped classroom on half-lives. As always, feel free to pause the video and take down notes. So half-lives are problems that deal with the concept of the fact that radioactive isotopes or radioisotopes will decay or decompose, and then there'll be less of it left. The exact definition of half-life is the amount of time it takes for half of a radioactive sample to decompose. So for example, let's say I had a 100-gram sample of something that was radioactive and it had a half-life of 12 days. That means that 12 days from now, instead of having 100 grams, I would have half of it, I would have 50 grams. And then in another 12 days, so in other words 24 days, that number would be cut in half again, and then I would have 25 grams, and so on. It would keep cutting in half over and over again. So what types of half-life problems can we come up with? Well, I can come up with at least 5 different variations of a half-life problem. But the good news is it doesn't matter how the question is phrased or even what the question is asking. If you're asking to do a half-life problem, the mechanism is identical. I don't use a formula, I just use a very simple system where I draw pictures and figure out what the result is. So let's jump right into it. Let me show you a half-life problem. This one says, how much of a radioisotope or radioactive sample remains from a 100-gram sample after 30 days if the half-life of the sample is 10 days. So immediately I recognize this is a half-life problem. It actually has the word half-life in it, and there are enough numbers in here to indicate that it's got to be done somehow mathematically. So let me explain using a simple picture. Let's make X the radioactive sample. I don't know what it is, so I'm going to call it X. If I knew what it was, I could give it its own name. Next to this X, I'm going to draw a very long line. And this line represents the time gone by. Now in this situation, we actually know how much time has gone by. It was given right here. It said it's been around for 30 days. So I'm going to write here 30 days. Underneath the X, I'm going to put 2 boxes. One box on this side, and this box is going to represent the amount I started with. So let's say amount started. On the other side of the arrow, again underneath it, I'm going to write another box, and this box I'm going to put amount left. So let's see if I can fill in either of these 2 boxes. The amount I started with, well, that was given. It said from a 100-gram sample. So clearly this is 100 grams. The amount that's left, I don't know, because it says how much of the radioactive sample remains. So I have no idea how much is left. That's what I'm trying to find out. There's only one more thing I need to put in this picture. And underneath this arrow, I'm going to put a series of smaller arrows, and these smaller arrows will designate the half-lives. The only problem is, I don't know how many little arrows to draw, how many half-lives have gone by. I do know that the half-life of this sample is 10 days, so let's start by just drawing one arrow and write on it 10 days. Though I do not know exactly how many arrows to draw at the moment, I do know this. If the entire time that went by was 30 days and the half-life is 10 days, how many half-lives have gone by in this 30-day period? Or what's 30 divided by 10? And that would be 3, so I'm going to draw 3 arrows. These arrows are all 10 days. They're 10 days long, and 10 plus 10 plus 10 is indeed 30. So this is the picture you want to have every time you do a half-life problem. You want to have your sample here, a long arrow designating the time gone by, the amount you started with, the amount you finished with, and a number of arrows to designate how many half-lives have gone by, which is always unknown. We never know that number, but we figured out just like I did just now. So here's the final part of the problem. How much is left after 30 days? Well, what happens to this 100-gram sample every 10 days? It gets cut in half. So what's half of 100? Well, that would be 50. So after 10 days, I have 50 grams. What happens after another 10 days? Well, that number gets cut again, and now I have 25 grams. And then what happens after another 10 days? Well, what's half of 25? 12.5 grams. And that would be my answer. Notice I didn't even need a calculator. I didn't really need to go to any reference table. I didn't need a formula. I just drew a picture and then did what I needed to do. So let's try another one of these half-life problems. This one says, how much time has gone by if 25 grams remains from a 400 gram sample of a radioactive isotope that has a half-life of 6 hours? Now that sounds like a complicated problem. There are a lot of words here, there are a lot of numbers, but I do recognize it's a half-life problem. As a matter of fact, the word half-life is in it. So let's do the same thing we did here. We'll start with an X. I don't know what the sample is, they didn't tell me, and I don't really care, to be honest with you. I don't need to have that information to solve this problem. I do know that this long arrow is time gone by, but this time I have no idea how much time has gone by. It wasn't given. How much time has gone by? Don't know. I do know that I started with 25 grams. No, I'm sorry. I ended with 25 grams because it says 25 grams remains from a 400 gram sample. So I ended with 25 grams and I started with 400 grams. Notice that now our picture here is looking a lot like our picture here. We have an arrow, we have starting, we have ending, we have time gone by that we don't know. What's missing from this picture though? The same thing that's always going to be missing. The number of half-lives. I need to know how many arrows to draw. But the truth is, I don't know. So let's just do one at a time and see what we get. Let's assume it was only one half-life. And again, remember the half-life is 6 hours. So what happens 6 hours from now? Well, my 400 gram sample gets cut in half, but is that going to be 25? Well, what's half of 400? That's only 200. So clearly I need to keep going. Another half-life has gone by. Another 6 hours. What do I have now? Well, half of 200 is 100. I'm still not there. Let's keep going. Maybe another half-life went by. What's half of 100? That's 50. I'm still not there. What about one more half-life? Well, sure enough, one more half-life, another 6 hours. Half of 50 is 25. So 1, 2, 3, 4 half-lives have gone by. And if each half-life is 6 hours, 6 plus 6 plus 6 plus 6, or 4 times 6, is 24 hours. An entire day has gone by. And that's my answer. All right, let's try a third type of half-life problem. This time, I'm interested in another bit of information. What is the actual half-life of a radioactive isotope that has been around for 15 years if 10 grams remain from an original sample of 80? Let's do the same thing we just did twice in a row. Start with an X. I don't know what the sample is. Then draw a long line. This time, do I know how much time it has gone by? Yep, 15 years. How much did I start with? Well, originally, 80 grams. Do I know how much I ended with? Yep. I ended with, after 15 years, 10 grams remained. So, once again, what is the only thing that's missing from our picture? The arrows. And once again, I have no idea how many arrows to draw. Maybe it's one arrow. Well, let's see. After one half-life, what would be left? 80 divided by 2 is 40. Well, it's not one arrow. What about another half-life? Half of 40 is 20. Nope, that's not it either. How about another half-life? Half of 20, yeah, is 10. So 3 half-lives have gone by. Well, if 15 years is the total, and there are 3 half-lives, what's 15 divided by 3? 5. So the half-life of this radioactive isotope is 5 years. 5 plus 5 plus 5 is 15. All right, let's try yet another half-life problem. This one's going to be a little different. This one is asking what fraction of a radioactive isotope remains after 12 hours if the half-life of the sample is 3 hours. Notice this time I'm not even asking for how much is left. I just want to know what part is left. But it's the same system. Let's draw an X. The time gone by is this time 12 hours. The only problem I have now is not only do I not know how much I started with, I don't know how much I ended with. So since I'm not given a specific number of grams, I'm going to put in here just the number 1. In other words, I have one sample. Now, other than figuring out how much is left, the only other thing that's missing is once again the arrows. But this one's going to be easy to solve because the half-life is 3 hours. Not hours. Hours. Sorry. How many times does 3 go into 12? 4 times, right? So that means 4 half-lives have gone by. And what happens to this sample every half-life? It gets cut in half. So what's half of 1? Half. What's half of a half? A fourth. What's half of a fourth? An eighth. And then finally, what's half of an eighth? 1/16 is left. Okay, final type of half-life problem I'm going to show you, and this one's going to be very, very different. It's going to be the same setup, but this time I'm not going to ask for a number. I'm not going to ask for how much time has gone by or the half-life or how much the original sample is left. I want to know if I have a radioactive isotope that's been around for 32.19 years and the original sample was 200 grams and there's now 25 grams left, what is the radioisotope? In other words, what is X? Don't worry, we're going to solve it the same way. The time gone by, 32.19 years. That's a lot. How much did I start with? 200 grams. How much did I end with? 25 grams. So once again, let's see how many half-lives it takes to get there. 1 half-life gets me to 100 grams. 2 half-lives gets me to 50 grams. And 3 half-lives gets me to 25. Half of 200 is 100, half of 100 is 50, half of 50 is 25. Which means that each half-life has to add up to a total of 32.19. And I'm going to need a calculator for this one because I know approximately the answer, but not the actual answer. So 32.19 divided by 3 is 10.73. So the half-life is 10.73 years. Well, great. I know the half-life. But that wasn't my question. My question is, what is the sample? How does getting this answer help me answer the question, what is the isotope? Well, this is where we can go to a reference table. There is actually a reference table, table N, that has not only a list of different radioactive isotopes, but their half-lives. So I'm looking for the one that has a half-life of 10.73 years. Let's see if we can find it. Nope. No. Still looking, Wait, what's that? 10.73 years exactly. KR85 has a half-life of 10.73 years. Therefore, our answer is potassium-85 has a half-life of that amount of time, and that is the answer. And that is how you do half-life problems.